Hello everyone, welcome back. Today we are going to discuss a medium level question from Leetcode called maximum width of a binary tree. Given a binary tree, write a function to get maximum width of the given tree. The width of a tree is the maximum width among all levels. The binary tree has the same structure as a full binary tree, but some nodes are null. The width of one level is defined as the length between the end nodes, that is, the length between the leftmost and the rightmost non-null nodes. One more thing to keep in mind is we should count the null nodes between the end nodes. For example, in the given binary tree, there are three levels. On level 1, the width is 1. For level 2, because we have two nodes, the width is 2. And for level 3, there are 4 nodes 5, 3, null, and 9. Therefore, the width is 4. Please note that we need to count null because it is surrounded by two other nodes which are not null, that is, node 3 and node 9. So, among these three widths, the maximum width we saw was 4. Therefore, the answer to this question is 4. Let us see another example. In this example, for level 1, the width is 1. For level 2, the width is 2 because we have two nodes, 3 and 2. And for level 3, the width would be 1. Please note in this case, we are not going to count null nodes because they are not surrounded by other nodes which are not null. That's why the width is only 1. And out of these three widths, the maximum width we saw was 2. Therefore, the maximum width for this binary tree is 2. The solution is not very intuitive, but if you read the problem statement carefully, then it might give you some hints. It says the width at any level is the length between the end nodes. This line suggests that we should consider the level or the depth while thinking for a solution. Okay? Now try to think. For any level, if we already know the position at which the leftmost node would exist, then for any other node which is also present at the same level, we can find out the distance between these two nodes by taking the difference between the position of these nodes, which is nothing but a width for any level. So now we have some intuition. We need to know the level and position for any given node. We can easily know the level or the depth of a node just by adding 1 to the level of its parent. Then we can apply any tree traversal algorithm, and for every node at level L, we find out the difference between its position P and the position of leftmost node at the same level L. But still, we have two problems. First, how do we know position for a node? And second, how do we know that a node at level L is the leftmost one? To know the position of a node, we must know the array representation of a binary tree. So, if we were to represent nodes of a binary tree as an array, then for any node at index I, its left child can be found at index 2i and its right child can be found at the index 2i plus 1. For example, consider a binary tree which represents values from 1 to 11. Now observe, for node 3, the left child is 6, that is 2 times 3, and its right child is 7, that is 2 times 3 plus 1. Now this property will hold always. Remember this for future. Second problem was, how do we know if a node is the leftmost one for any level L? The answer is simple. We maintain a hash map or a dictionary where key would be the level and the corresponding value would be the position of a node. Because we know that we always visit left child first, that's why whenever we see a node at a level L and at position P, we perform a lookup into the hash map. If we see that the hash map contains a key equals to L, it means that we have already visited this level and the current node is not the leftmost one. Otherwise, if we do not found a key L in the hash map, then we can say we are visiting this level for the first time and this current node is the leftmost one. And after that, we need to update our hash map accordingly. So I hope the entire logic is very clear to you, and if not, then we are going to see a proper algorithm. After that, all your doubts would be answered. So first we will know the depth and the position of a node like this. After that, we maintain a hash map which tells us the position P of the leftmost node at the level L. After that, whenever we see a node, we perform lookup into the hash map to know the position of leftmost node at the same level. If we find any such node, then we calculate the difference between position of these two nodes. If we do not find that level L into the hash map, it means we are visiting this level for the first time, and this node is the leftmost node of this level itself. So we update our hash map. Just read out this algorithm and you will know what I mean. We maintain a hash map to store the position of leftmost node at level L. We also maintain a variable to store the maximum width seen so far. Initially, the hash map would say that at level 0, the position of the leftmost node is 0, because we know that at the top we only have one node which we call root node. Because at level 0 we have only one node which is known as root node itself. Now, it really doesn't matter how you choose the initial values of level and position because everything is relative. At the end, we are just going to calculate the differences. Then we define a method which accepts a node, its depth, and its position. And this function is going to update the global answer whenever we find a larger width or larger difference between the position of the end nodes. Let's see how it works. If node is not null, then we check if we are visiting this level L for the first time or not. If we are visiting this level for the first time, it means that the current node is the leftmost node of the current depth. Otherwise, we find the distance between the position of our current node and the leftmost node at current depth. And if this difference is greater than the previous answer, then we are going to consider this difference as the current best answer. After that, we are going to apply same method on the left child and on the right child. The new depth would be current depth plus 1, and we also need to update positions of the left and the right child. And that's it. You have just solved maximum width of a binary tree. If you like this video, please hit the like button and subscribe to my channel. Bye.